Hey everyone, we're continuing our discussion of regression assumptions and model evaluation based on one of the applied examples that is included in our textbook reading. And what we're going to look at specifically is we're going to fit a series of regression models predicting cognitive test scores of preschoolers given characteristics of their mothers. Okay, and this is based on data from a survey of adult American women and their children, which was a subsample or is a subsample from the National Longitudinal Survey of Youth. Okay, so our goal is to predicting the children's test scores on this cognitive test. Okay. The data is of course also available on RStudio Cloud, so make sure to follow along as you watch this video. Okay, here's a quick overview. We load of course using the tidyverse, load the underlying the CSV data file, and we see we have 434 observations and 5 variables. Our outcome is the kid's cognitive test score, and we have a couple of predictors. We won't use all of them in this example, but we'll use them throughout future videos as well. The only thing I'm doing here in terms of recoding is I'm changing the mom underscore HS, which is a dichotomous indicator, which is equal to 1 if the mother has a high school degree and 0 if the mother does not have a high school degree. From that numeric dummy indicator, I'm just changing this to a factor that is either no or yes, which will be useful later on just for plotting purposes. Okay. In terms of actual regressions to predict, or regression models to predict those test scores, there are 4 different types of models that we are going to look at, or we can look at. The first one is a single binary predictor. We're just including the dichotomous indicator for high school education or mother's high school education as the only predictor. We have a single continuous predictor where we just include the mother's performance on an IQ test as a predictor. We have a third model where we include both predictors, so high school education and the IQ test results, as well as in an interaction. If we kind of hypothesize or are interested in examining whether, for example, the effect of, or whether the relationship between the mother's IQ and the child's test score is somehow conditional on high school education, for example. Okay. I'm not going to go through all of these models in detail. Make sure to kind of check out those results as well, and also when it comes to kind of interpreting those regression results, make sure to review chapter 10 in our required textbook as well, where there's a little bit more discussion of how to interpret regression coefficients and so on. Okay. In terms of kind of interpreting the model fit and evaluating how well the model actually fits the data, the first thing, of course, we want to do is look at the parameter estimates and then ultimately plot the data and the fitted model. Okay, so if we just now focus on the 4th model that includes our interaction term and both predictors, we can briefly look at the parameter estimates, but one thing we should keep in mind in this case is that a lot of the coefficients here are not directly interpretable because we didn't mean center any of our predictors, right? So, for example, the mother's IQ test scores ranges somewhere between probably 70 to 130. And we include an interaction here between mother's IQ and high school education. So that means that, for example, the coefficient for high school education indicates the expected difference in the children's test score conditional on the IQ being equal to 0. Similarly, the intercept indicates the expected outcome, the expected test score of the child for if the mother's IQ is equal to 0. And of course, there's no observation with an IQ of 0. And so this is a clear extrapolation out of the range of the data, right? So what we would do if we wanted to directly interpret those coefficients, we could mean center our predictor, mom underscore IQ, and to make both the high school coefficient and the intercept directly interpretable. Again, a lot of that discussion is in chapter 10 of the textbook, so make sure to check that out if you want to kind of refresh your memory on that, and also check out the additional lecture videos, old lecture videos that I have on interpreting regression coefficients, right? For now, it's sufficient to say that linear combinations of, or linear transformations, I should say, of individual predictors doesn't change the model fit, right? So, you know, mean centering a predictor has changes to what extent the coefficients are directly interpretable, but it doesn't change how well the model actually fits the data, okay? And so for now, when we're just talking about model fit, we can just work with these models, okay? The first thing we want to do if we want to evaluate how well this model fits the data is to plot the raw data along with our fitted regression line, okay? That's kind of a first check of what exactly, you know, how exactly the data are distributed, and also how well our model ultimately fits these data. And in order to do that, and in addition get an idea of the uncertainty around our regression line, what we're going to do is we're going to take a couple of random draws from our simulated posterior distribution. And we can do this by just converting our model object into a tibble, as we have done in previous videos. But remember that these simulated draws from the posterior distribution contain, if you use default settings for Stan GLM, 4,000 draws from the posterior distribution. We don't need as many draws, so what we do is we just take a random sample of 25 of those draws, okay? So the resulting tibble is a 25 by 5 tibble that contains 25 separate draws from the random draws from this posterior distribution, and each kind of each draw contains one intercept, one and 4 different parameters, 3 regression coefficients, and the error variance. Okay, so we have for each, as we talked about last week, we have for each kind of simulation, we have a draw. For each simulated draw, we have a set of regression coefficients and estimated parameters that we can use to visualize the uncertainty around our fitted model, okay? And so the way we do this, oops, wait a second, is right here, we taking into account this interaction between high school education and the IQ score, we're plotting the data directly split up between observations where the mother has a high school education and where the mother does not have a high school degree, and then include separate fitted lines based on these parameter estimates to visualize the relationship, the association between the IQ score and the child test score, right? And so we not only include kind of the best fit line, which is the posterior median for the slope and the intercept and the interaction, but we include kind of separate, you know, smaller lines for each of those simulation draws to kind of visualize the uncertainty around our estimates. As always, the code to generate this specific plot based on our coefficients as well as our draws from the posterior distribution is available on RStudio Cloud. Okay, so after we kind of took a first look at the raw data and included our fitted regression lines, the next thing we want to do is we want to plot the residuals so the kind of the deviation between our predicted value and the actual observed value versus our fitted values. Okay. The basic idea here is that if the model is correct and if these assumptions that I mentioned in the previous video kind of hold, specifically regarding linearity and so on, then the residuals should look roughly randomly scattered around 0 across the entire range of fitted values. Okay, and so in order to kind of evaluate the residuals, the plotted residuals versus the fitted values, what we're going to do is we're taking our original data, kid IQ, and we're adding two different variables. First, we're adding y hat, that's just our vector of predicted values, which we're generating using the predict command, and we're adding our residuals, which is just using the residuals command. And we're just adding those to our original data frame. Okay, and then we're adding a ggplot call where the static mapping for the y-axis is the residuals, and for the x-axis is y hat, so the actual predicted or fitted values, so to speak. We then add a horizontal reference line for to indicate 0, because the errors, of course, or the residuals, I should say, should be centered around 0 and should just, you know, scatter randomly around that line. We're adding another geometry, the points, of course, for the residuals and the fitted values, and then add some additional arguments to make the plot look a little bit nicer. Note here that I'm also adding a facet. I'm splitting this up now for high school and no high school, the high school and no high school group, so to speak. We could also look at the plot just for the combined sample and evaluate it based on that. But sometimes splitting it up for these groups makes it a little bit easier to spot if there are problems with one specific subset of the data, for example. Okay, and so this is the result. Of course, we have on the top here, we have the observations without a high school education, and on the bottom we have observations with a high school education, and we see this horizontal 0 line, and we see basically what we want to see, which is the residuals are along the range of predicted values. The residuals are kind of randomly scattered, centered around 0, and there's no sign of, for example, heteroscedasticity, where we would have a larger variance for some area and a smaller variance for another area, or nonlinearity, where we have clear, you know, systematic patterns where there are residuals that are more likely to be positive for some range and more likely to be negative for another range, or something like that, right? So as long as this looks fairly randomly scattered, we're kind of fairly confident that at least these basic assumptions about the regression model hold. Okay. So this is only based on model 4, right? If you want, as an exercise, you can check out similar plots for the remaining 3 models. Okay, model 1, 2, and 3. Okay. So far, what we did with the predicted versus the residuals versus fitted plot was to kind of evaluate this basic, some of these basic like linearity assumptions and constant error variance assumptions that are kind of fundamental to the linear regression framework. There's another additional way of kind of checking how well the model actually fits our data, and that basic technique is called posterior predictive checking. Okay, the idea behind posterior predictive checking is to basically take our model and then simulate replicated data sets under the fitted model and then compare these to the observed data, right? So the underlying idea is we take the model that we estimated and we generate new, fake data, assuming the data generating process of the model that we specified, and then compare the distribution of kind of fake data against the actual observed distribution. And this can help us identify if, for example, functional form assumptions or other misspecifications or other kind of specification errors occur. Okay, so the way we can do this is we can extract our observed outcome variable, and we'll just save this in a vector y. And in addition, we create an additional this will actually be an array y rep, which is now kind of a set of draws, basically predictions, posterior predictions. So basically, we're taking our model, and for each simulation draw from that model, for each draw from the posterior distribution, we create a set of predicted values for y based on the data that we have. Okay, so of course these kind of a replicated fake datasets take into account the modeling uncertainty, and they are basically allow us to visualize the implications of our assumed underlying model and our assumed kind of functional form. Okay. The first thing we can do is we can look at the estimated densities of the predicted values based on our fitted model and compare that with the actual distribution of the outcome variable. And the way we can do this here is use the PPC, which stands for Posterior Predictive Check density overlay. This is part of the Bayes plot package, which I showed you in our Q&A sessions. For both the actual observed y and our simulated fake data. And we're just focusing on 50 separate kind of iterations rather than 4,000 as similar to the previous example. Okay. Maybe I'll discuss this. This is the result of this first plot you'll see on the top here. And so the underlying idea here is we have a distribution of outcome measures, right? So this is our, the dark blue line is basically our actual observed y, okay? The distribution of our actual observed y, right? So, so the kid's test score here ranges between 40 and something around 120, and it's not quite normally distributed. There's a little bit of a fatter tail, so there are a few more kind of outliers towards the bottom end of the distribution, but that's the actual outcome measure that we observe. Okay, and now we fitted our model, we ran our regression, and then we take our draws from that posterior distribution and generate new fake data, right? And based on that fake data, we can make predictions for our set of observations that we have, okay? And so based on our fitted model, we can basically plot like a simulated distribution of outcome measures for each of those models, okay? And so what we see here is basically 50 different densities that are based on our fitted model, and those are the posterior predictions based on the model and the data that we actually observe, okay? To the extent, so of course this doesn't 100% resemble the observed distribution, but to the extent that there are like severe misspecifications in terms of the underlying functional form or underlying distributions, then our observed distribution can deviate strongly from our posterior predictive distribution, right? So here, even though there are some slight variations and deviations, the fit overall is quite quite okay. Rather than just looking at the difference between the estimated densities and the predicted the estimated densities of predicted values and the observed data distribution, we can also specify certain test statistics and look at the distribution of test statistics versus the observed test statistics. So for example, suppose you were interested in evaluating or in your predictive task, what you're really interested in is the proportion of kids that received a test score of more than 100 points, okay? And so what we can do is we can write a quick function, which I'm just going to call prop 100, that is just equal, for a given set of observations, just computes the proportion of observations that are larger than 100, okay? And so now what we can do is kind of, using the same logic, we have our observed data. In our observed data, we have a given proportion of observations of kids who scored higher than 100. And now we're using our posterior predictions based on our model fit. And for each of those posterior predictions and for each of those draws from our simulated posterior distribution, we compute the same test statistic and then look at the distribution of test statistics across our posterior distribution draws. Okay, this is we can plot this directly using PPC stat. So this is again part of the base plot package, and what we see here is the result is on the bottom half, and we see the vertical line that indicates the actual observed test statistics. So in our data we have about 27% of the kids scored above 100 on this specific test score, and under our assumed model, based on our posterior predictions, we can see that this is quite within the range of what we would expect, kind of observing such a test statistic wouldn't be unusual under our kind of assumed model with our posterior predictive checks. Okay, so again, this kind of illustrates that our model fits the data fairly well. If this test statistic was widely outside of our distribution, then we would say, okay, there might be something that we're missing in terms of fitting the underlying kind of matching the underlying data generating process. And in the textbook you have some examples where we have deviations like that. For example, measuring, there was one example measuring the speed of light, for example, where you see the distribution of a test statistic that is widely outside of the range of posterior predictions. So those are kind of two basic techniques. On the one hand, plotting residuals versus fitted values, and on the other hand, posterior predictive checking, that allow us to evaluate whether our model, fits the data reasonably well, right? Or whether there's some misspecification, some functional form assumption, or some issues with our linearity assumptions, where somehow kind of our assumed model doesn't fit the underlying real world data generating process. Okay. In the next video, we're going to go a step further, and we're going to look at model selection and how we can use cross-validation to compare two competing models and pick the one that ultimately has more predictive power.